Okay, so suppose we have some fluid. Rho represents the density of the fluid, and V represents the velocity vector field of the fluid. Okay, so both the density and the velocity field will be functions of x, y, z, as well as a function of t, so a function of time. V being the velocity of the fluid will have three components: an x component, a y component, and a z component. All right. Now to to model how a fluid will flow, um, if we make the assumption that in a small element of volume, so imagine this is like a small cube. If we make the assumption that in the small element of volume, the mass is conserved, okay? Mass being conserved means that the rate of change of mass within this cube should be equal to 0. Now, there's going to be two sources of change in the mass in this cube. So one, the mass could be changing due to a change in density. And then another source of change in mass is the mass flux, which is mass flux just means how much mass is entering the cube, say from the fluid flowing into it, and also like how much mass might be leaving the cube from fluid flowing out of it. So the mass flux is the net amount of mass that's coming in or out. Okay. Now, with this assumption that the mass is conserved, that leads to something called the continuity equation. Okay. So here I'm not going to go into all the little details of the derivation of this, but essentially this first term in the continuity equation, this is just the rate of change of the density with respect to time. So this first term is representing the change in mass that might occur due to a change in density. And then the second term in the continuity equation, so this term here, so this is the divergence of, and then here inside the parentheses, we have the density times the vector field. So this second term, the divergence term over here, this is measuring basically the mass flux, or how much mass is entering and leaving the cube over time, okay? And so we're saying the total rate of change of mass should be equal to 0 under our assumption that the mass is conserved, okay? So that's what this continuity equation is coming from. It's coming from conservation of mass. Okay. Now, if we assume that the flow is steady, okay? Steady flow just means that the rate at which the density is changing over time is 0 within this volume element. And if this is 0, then the continuity equation reduces to just one term on the left. So this term goes to 0 for a steady flow. And we just have that this divergence of the density times the velocity field should equal 0. So this is kind of like the general continuity equation. And for the special case where you have a steady flow, the continuity equation simplifies down to just this equation. Now, for an incompressible flow, So the key physical assumption for an incompressible flow is that the density within a volume element, so within like a tiny cube, we assume that the density can be treated as a constant for incompressible flows. And because we can treat the density as a constant within that little cube, first is this term will be 0 if the density is constant. And second, the density here in the parentheses could be factored out if it's constant. And then you could divide it out of the equation. So for an incompressible flow, the continuity equation simplifies even more as just the divergence of your velocity field should equal 0. Okay? Okay. Now, remember that the divergence of a vector field in terms of the usual XYZ coordinates, the divergence was just the partial derivative of the x component with respect to x plus the partial derivative of the y component with respect to y, and then plus the partial derivative of the z component with respect to z. Okay. So if v was the velocity field for an incompressible flow, then we're saying its divergence should be equal to 0, meaning that this equation should be satisfied. And the divergence in terms of cylindrical coordinates, the divergence is given by this expression. Okay. So for an incompressible flow in cylindrical coordinates, you would have that this equals 0. Okay. All right. Now in 2 dimensions, so in 2 dimensions, you wouldn't have a z component, so this term would just disappear. And so therefore in 2 dimensions for an incompressible flow, you would have that this must be equal to 0. Okay. All right, now let's suppose that we have some function c, okay? And this function is just a scalar valued function, so a scalar field. Okay. So this is just like any function, no connection to what we talked about at the moment. Okay. So let's just suppose we have some random function c, and then from this function c, I'm going to define a vector field v. Okay. And so this vector field v is defined as follows. So the x component is the partial derivative of z with respect to y, and the y component of v is the negative of the partial derivative of z with respect to x. Okay. So for this vector field v, what I'm going to do right now is I'm going to calculate its divergence. Okay. So remember that the divergence of a vector field, you take the partial derivative with respect to x of its x component plus the partial derivative with respect to y of its y component. Okay. So now here, this will just be the second order mixed partial derivative of c with respect to y and then x. Here you can factor the minus sign out in front. And then this is just going to be the second order mixed partial derivative, but with respect to x followed by y. Now, as you may recall, these second order mixed partial derivatives are going to be equal to each other. So it doesn't matter if you do the derivative with respect to x and then y, or the derivative with respect to y and then x, they should be the same. So therefore, these two are going to cancel out, and you'll be left with the divergence of this vector field v as being equal to 0. And because the divergence of this vector field v is 0, that means that v could be thought of as the velocity field for an incompressible flow. Okay? Because remember that for an incompressible flow, its divergence must be 0, which in 2 dimensions means that this must be satisfied. And here we've proven that for a vector field defined as such, its divergence is going to be 0. So therefore, you can think of it as the velocity field of an incompressible flow. Okay? Now, what I did here just now is I started with some function psi, and then using this function psi, we were able to create an incompressible flow v from it using this formula. Okay. So now, a question that you may have is, can we sort of reverse that order? So can we instead start with an incompressible flow v, and then if we have an incompressible flow v, can we say that v was equal to this for some function c? Okay. And so the answer is yes. Okay. I mean, assuming that like your functions are all nice and smooth or whatever. Okay. But generally, the answer is going to be yes. So such a function c is called a streamline function. And we'll talk a little bit about the significance of the streamline function in just a bit. Here, I thought I would do maybe a really simple example of finding the streamline function for an incompressible flow. So here I've created a vector field v right now. And so first, let's compute the divergence of v to check if it is incompressible. So remember the divergence of v, we take the partial derivative with respect to x of the x component of v, and then plus the partial derivative with respect to y of the y component of v. Okay, so here the partial derivative with respect to x, that's 2x. And here the partial derivative with respect to y is negative 2x. Okay. So we see that everything cancels out, and so in fact the divergence of v is equal to 0. So since the divergence of v is equal to 0, that means that v is an you can think of v as the velocity field of an incompressible flow. Okay. And I'll just shorten that by saying that v is incompressible. Okay. So now, since v is incompressible, we should be able to find a streamline function for it. So that's what we're going to do next. We're going to find a streamline function c. So remember that the streamline function is supposed to satisfy the property that the partial derivative of c with respect to y should be the x component of v, and then the y component of v should be the negative of the partial of c with respect to x. Okay. So then that means the partial derivative of c with respect to y needs to be equal to x squared plus 4y. And then the so negative of the partial of c with respect to x needs to equal 3 minus 2xy. And from that, we will get that the partial derivative of c with respect to x should equal the negative of this. So then the negative of this, I'm just going to change the sign of everything. So I'll make it 2xy minus 3. Okay. So now what we want to do is we want to use these two equations to find our streamline function. So what we can do is we can take, maybe let's just take this first equation. So this is the partial of c with respect to y. So if I integrate this with respect to y now, I should recover the streamline function c. So we're just going to integrate x squared plus 4y with respect to y. So that's going to be x squared y plus 2y squared. Now, however, here, when we did the integral with respect to y, we were treating x as a constant. So we should add like a plus c at the end, but that plus c could actually be a function of x. So to emphasize that, I'll write plus c of x. Okay. So we integrated this with respect to y to recover the streamline function, but right now we're not finished because we haven't figured out the streamline function completely yet. So we don't know what this function c of x is, and therefore we haven't quite figured out the streamline function completely. So to figure out what c of x is, we want to make use of this second equation that we had as well. So the way that I'm going to make use of this is I'm going to take what we have for c right now, and I'm going to calculate the partial derivative of c with respect to x. So the derivative of this with respect to x will be 2xy plus c prime of x. So now I have two expressions for the partial derivative of c with respect to x. So these two need to be equal to each other. And so for these two to be equal to each other, it must be that c prime of x is equal to negative 3. Because we have a 2xy for each of them. And then we have minus 3 over here, and plus c prime of x over here. So c prime of x should be equal to negative 3. And so integrating with respect to x, that means c of x itself should be negative 3x. Now here you could also add a constant to this, but at this point we don't care about that extra constant. So it's good enough to just say that c of x is negative 3x. So now we're gonna, I guess, take that result and plug it into the expression up here for c. So ultimately, what we find for the streamline function c is that it's equal to x squared y plus 2y squared, and then plus c of x is minus 3x. So then that gives us our streamline function, or at least this is a streamline function, okay, for the original incompressible flow that we started with, okay? All right. So that's just a quick example. If you start with an incompressible flow of how you might try to find a streamline function for it. So now I just want to talk a little bit about, I guess, the importance or the significance of having a streamline function. So I guess the key fact about a streamline function is that the contours of the streamline function, so those are called the streamlines, and these streamlines, what they represent is the path that a small object would travel along when placed in the fluid flow. So I thought I would maybe just illustrate that with an example that we can sort of explicitly see. So here is the example that I decided to use to illustrate with. So here I'm going to start with a streamline function psi. And so psi is just going to be x squared plus y squared. Now the incompressible flow v associated with psi. So this is the formula. The x component should be partial of psi with respect to y. Y component of v should be the negative of the partial of psi with respect to x. So here, partial with respect to y would be 2y. Partial with respect to x is 2x, and then we have the negative in front of that. So first, if you just start trying to sketch this vector field v, okay? So remember the way that you can sketch a vector field is you take some points and you plug it into your vector field v. So here I just took 3 points to start with. So the point 1, 0, plug in 1 for x and 0 for y into v over here. So 1 for x, 0 for y, you'll get 0, negative 2 for v. So then what you do is at the point 1, 0 in the xy plane, so here's 1, 0, we would attach to that point the vector 0, negative 2. So this vector 0, negative 2, it points purely in the negative y direction, so points purely downwards. If I take the point root 2 over 2, root 2 over 2 for xy, we plug these in for x and y over here. You'll get that v is square root of 2 and then negative square root of 2. So at this point, root 2 over 2, root 2 over 2. So this point would be at a 45-degree angle along the unit circle. We want to attach to that point the vector root 2 minus root 2. So this vector, positive x component, so it points towards the right. Negative y component, so it also points downwards. So then that vector looks something like this, pointing to the right and also downwards. I could plug in the point 0, 1 into v. So if x is 0 and y is 1, x is 0, y is 1, you get the vector 2, 0. So at the point 0, 1, so the point 0, 1 is here. we're going to attach to that point the vector 2, 0. So that vector points purely in the positive x direction, so pointing purely towards the right. Okay. So if you were to plug in more points into V and then draw the corresponding vectors attached to those points, those will give you a picture of V where those vectors would kind of seem to be kind of circulating around the origin like that. Okay. All right, now if you look at the streamline function, so x squared plus y squared, so the contours of the streamline function, those are just the curves that you get when you take your function and you set it equal to a constant. Okay. Now in this case, x squared plus y squared equal to a constant. So that just describes the equation of a circle centered at the origin. So the contours of C are going to be circles centered at the origin. Okay. So here you see that the contours of the streamline function C correspond to the sketch of our vector field V. Okay. So the idea is if you were to take like a tiny object and you were to place it, say like at this point, okay, then that object is going to be pushed along this circular path by the fluid V. Okay. So if you were to plot the contours of a streamline function, the contour map would kind of show you how the fluid is flowing in the plane by showing you how an object is going to be pushed along that flow. Okay.